Hello everyone. My name is Chernam Zamiri. I'm gonna be taking you through introduction, background research, and problem. So the purpose of our project is to design research. So modern lending institutions increase. Lending institutions face two central challenges.
For specification and design of our predictive model, we be um, so after we predicted each borrower's default probability, um, and so from the sensitivity analysis that we did, acquisition stage. Um, so onto the descriptive results. So to better um, our analysis extended to we also analyze credit related variables, employment. Um, these are just measures of central tendencies, which will the data better. And so, from all this, one of the most important findings um, for our data transformations, our main goal was to
Hello, my name is Enobong Etuk, and I'll be taking the results all the way through to the conclusion. So we start off with hyperparameter tuning. The hyperparameter for our model was the threshold. The threshold is the value above which an observation is classified as a default. Initially, we started with a value of zero point 0.5, which in practice does not make practical sense because it would mean that we are giving equal costs to misclassification of defaults and non-defaults. Whereas in real life, in the real world, misclassifying defaults are way more costly than misclassifying non-defaults. So we charted different metrics. As you can see from the graph, we charted them as we reduced the threshold, and based off of that, we selected our optimal threshold based on our business case. Sensitivity was selected as the primary metric because of the high cost attributed to misclassifying or missing a default. In lending, missing a default, which is a false negative, is far more costly than incorrectly flagging a non default, which is a false positive. So, in a selection of an evaluation metric, we had to ensure that we selected one that could quantify false negatives. So, we selected at recall, which measures the ability of a model to correctly identify defaults. And it's critical for minimizing financial risk by catching high risk loans. And in addition, we selected the F1 score as a complementary metric. The reason being for different thresholds that could have the same or similar sensitivity, we could use the F1 score as um, as a secondary level of evaluation to select which model performed or which threshold rather performs better. The F1 score balances precision and recall and is it works well with data sets that are imbalanced like ours. So our final decision was to prioritize sensitivity over recall due to the cost of missed defaults and also using the F1 score as a secondary evaluation metric. So next we have a look at the confusion matrix that a selected threshold of 0.1 outputted. So we dive into the details of the result of a confusion matrix. We are concerned about true positives and false negatives. So we could see that a model was able to classify 4,411 defaults correctly and misclassify 8,519 defaults. This gave us a sensitivity of 74.4%, which shows a strong ability of our model to catch actual defaults. Although there was a trade-off between sensitivity and specificity. So basically, a higher sensitivity meant that fewer missed defaults, and this actually aligns with the risk management goal. But a lower precision was acceptable because false positives only trigger a manual review and not financial loss. And this confirms that threshold of 0.1 prioritizes risk management over operational efficiency. So now we take a step back and look at a model's performance at different thresholds, how it compares to random guessing. So our logistic model was evaluated using the confusion metrics, as we mentioned earlier, and the ROC curve. So the confusion metrics looked at how our model performed at a selected threshold, while the ROC curve looks at how evaluates a model over different thresholds. So we had an AUC score of 0.7426, indicating strong discriminatory power. What does this mean? AUC is area under the receiver operating characteristic curve. It measures the model's ability to distinguish between different classes, in our case, defaults and non-defaults. Higher AUC indicates a better ranking ability across all possible thresholds and confirm the model is reliable for threshold tuning decisions. So it ranges from values for AUC range from 0.5 to 1, with 0.5 being as good as random guessing, and 1.5 means the model is perfect. So a model evaluated to 0.742 AUC, which is pretty good. And it's also fair to mention that AUC is threshold independent, so it basically evaluates the model's ranking ability before a specific cutoff is picked. So looking at the overview of the optimization, we created a synthetic data set of 1,000 loan applications using Python. We fed it to our model, and our model assigned probabilities of default on each one of these applications, which led to either an approval or a rejection of these loan applications. The optimization framework then selected a subset of these loans that maximized our expected portfolio profits while ensuring all lending decisions were met. So the values of our simulations are outlined in the table on the slide. So we assume that we started with 10 million of available capital, and is noteworthy to point out that our interest rate ceiling was redundant because it's a regulatory constraint, and hence we cannot vary it. So we only used our budget, which is the loan deposit ratio, and our default rates as our binding constraints. Having a look at the optimization results, we can see that the default rates constraint is not binding. This is intuitive, as our loan application goes through two filters. The first, which reduces the probability of default, and the second which optimizes the profit. So high risk loans are not selected. So basically we do not need a default rate constraint. And then secondly, the budget constraint is binding on the other hand, and it turns out that increasing the LDR directly increases the number of approved loans because we have more money to lend, and this in turn increases the profit, and our profit increases approximately $10,825 for every 1% increase in the LDR, making capital availability the primary driver of profitability. So the integrated results of the prescriptive and predictive analysis shows that selecting a threshold of zero point 0.1 is desirable, although there's a reduced overall accuracy because more non-defaults are flagged as defaults. The model's ability to identify true defaulters is is increased. So why are we comfortable with this trade-off, you may ask? That's because investigating false claims has a minimal cost or loss compared to missing a default. Also, on the optimization side of things, yes, LDR is the primary driver of profitability, but there's no optimal LDR. So it turns out that the higher the LDR, the higher the profitability, and the lower the LDR, the lower the profitability. So we came up with the following recommendations in conclusion. A threshold of 0.1 will be used to maximize sensitivity and reduce the cost of overlooking an actual defaulter. So the rationale behind this is that lower thresholds improves the detection of high risk loans, and the financial cost of missing a default is greater than the cost of false positives. And then we would come up with we also recommend that a risk-based loan approval policy is put in place based on our model. If the default probability is less than 0.1, then the loan is approved. If the default probability is greater than 0.1, then the loan is flagged either for manual review or for rejection. The pros of this is that it's simple, transparent, easy to communicate, and integrates directly with our prescriptive optimization model. The impact of this for the business is that it's going to capture more true defaulters, and it will support safer lending decisions. Although it would increase operational load due to the fact that manual reviews would be increased. And also for the LDR, since there's no universal best, we recommend that the industry average of 85% should be adopted to maximize probability, and it should be supported by prudent liquidity management, a prudent liquidity management system, so the business is able to meet its short-term obligations. So we also recommend that our model should be, before deployment of our model, we should conduct a pilot for just 1 quarter to assess the real world outcomes to ensure minimal disruptions in our operations. So during the pilot, the following will be monitored: actual and predicted default rates, number of manual reviews triggered, losses avoided, changes in approval volume and portfolio mix, the profit impact on that chosen LDR, and operation workload from false positives. And after the pilot, we'll recalibrate. If we have too many defaults missed, we'll lower the threshold further. If the operational load is too high and the cost of false positives is increased, would have to lower the threshold slightly and then reassess the LDR if liquidity or profitability deviates from our projections. So the integrated predictive prescriptive framework will combine model-based risk scoring with clear decision rules. It will optimize the portfolio, it will improve safety, profitability, transparency, and accountability, and then it will support continuous learning through pilot testing and positive and monitoring. And so we hope to achieve more profitable and more responsible lending decisions. Thank you.